Hello, everyone. My name is Akihiro Hayashi. I'm a senior research scientist at Georgia Tech. Today, I'll be talking about accelerating CHAMPS on GPUs. Okay, let me first talk about what CHAMPS is. CHAMPS is a computational fluid dynamics application that is originally written entirely in CHAPL. It is a 3D unstructured finite-volume Reynolds Average Navier-Stokes and potential flow solver using a self-centered discretization. CHAMPS is developed at Polytechnique Montre, and we at Georgia Tech are currently working on the potential flow solver. In this talk, we discuss our experience in accelerating CHAMPS on GPU using our GPU API and GPUIterator modules. Although our CHIUW 21 talks was more about proposing the GPU API module and we used the CHAMPS as an example, this year, we dive into more details of our GPU implementation. We also propose an additional optimization, and we present performance numbers on different platforms, including a new platform. What you see here is a rough end-to-end flow of CHAMPS. At a very high level, it constructs an equation based on the model file, and it solves the equation. As you can see, there are 4 steps, and I will explain each step one by one. The first step is the initialization steps, where it prepares the data based on the model file. Then the next step is the assembleLHS part, where the left-handed side of the equation is constructed. And similarly, the right-handed side of the equation is also constructed in the third step, which is assembleLHS. And finally, the equation is solved in the BigStab part. And the character in the LEDs are providing a result on a single node of the Cori. And as you can see, the assembleLHS part accounts for around 90% of the end-to-end execution time, and the BigStab part accounts for around 9% of the end-to-end execution time. So we basically accelerate the assembleLHS part and the BigStab part using GPUs. And here's a high-level summary of our GPU implementations. The assembleLHS part contains 2 for while loops, for which we implemented the CUDA version and call it from CHAPL using our GPUIterator and GPUAPI modules. The BigStab part essentially called the LAPACK dgesv, which solves a linear equation using an LU decomposition, for which we utilize a highly optimized GPU solver, which is CHIUW solver and the cuBLAS. And let me now talk a little bit about how we implemented the GPU version of the assembleLHS part. Essentially, for each for while loop, we use our GPUIterator module to call our GPU kernel from it. And for those who are not very familiar with the GPUIterator module, let me elaborate a little bit more about it. The GPUIterator is a user-defined parallel iterator that can be executed with CHAPL's for while loop. And if you take a look at the code on your right, you see the original for while loop on line number 3, and the GPUIterator version of it on line number 6 to 7. You can see that the GPUIterator wraps the original iteration space with 2 additional arguments. Essentially, the GPUIterator divides the original iteration space into 2 spaces. One is the CPU space, and another is the GPU space by using the CPU% on line number 7. For the CPU space, the body of the original for while loop is executed on CPU, and for the GPU space, it invokes a user-provided callback function in which device memory allocation, data allocation, host to device, device to host, data transfer, and kernel invocations are performed. So one of the most challenging problems in preparing our CUDA version was that interfacing CHAPL object to the CUDA part, because CHAMPS is implemented in an object-oriented way. But in the CUDA part, it is typically convenient for us to use an array of primitive types. So we had to do some sort of serialization so the CUDA part can handle CHAMPS data easily. And what you see here is a very simplified version of CHAMPS mesh data structure, which has a definition of class zone, which is a part of the entire mesh, and it includes one scalar variable and one array with a length of n. CHAMPS use an array of this kind of structure, and each for loop typically use data across multiple zones. And let me introduce two typical zero access patterns in CHAMPS. The first pattern is what we call the array of scalar pattern, in which the scalar member of all the zone is accessed in a single for loop. And the second pattern is what we call the array of array pattern, where the array members of all zone is accessed in a single for loop. And essentially, we facilitated the serialization part by utilizing our GPU API module, and I'll give you more detail in the next couple of slides. Okay, so let's talk about the array of scalar pattern. This pattern basically deals with the multiple scalar variable, and we did some pre-processing so they can be packed into the single chapel array, as you can see on your left. And for those who aren't very familiar with our GPU API module, the module essentially provides a multi-level chapel GPU API, which helps the user to write the device memory allocation, reallocation, host to device to host data transfer in chapel. And currently, we have two tiers of API, mid-level and the middle-level API. And we would say the mid-level version is the bit more chapel programmer-friendly version, because the user can use their new keyword to allocate GPU memory, whereas the mid-level is more like a thin wrapper for the low-level GPU API routines, such as the CUDA routines. And going back to this example, at the mid-level API, you allocate the device memory by just putting the chapel array into the construct of the GPU array structure and call the to-device function to do the host-to-device transfer. And at the middle level, the code is a bit more complicated, as you have to deal with the low-level types like a C void pointer and so on. Also, I didn't put any example here, but we also have a low-level version of this code, which is a full CUDA version, in which the user has to write an even lower level code than the mid-low level API. Okay, so let's talk about array of array pattern. Similar to the previous slides, we have a dedicated class for creating an array of array on GPU, which is called the GPU jagged array. And if you compare the mid-level API version with the mid-low level API version, you see that the mid-level version significantly simplifies the array of array allocation on GPU. And now let me talk a little bit about the kernel implementation. Technically, the two for loops in the assembleLHS part is a triply nested for loop. However, in the current GPU implementations, we only parallelize the outermost loop, where each CUDA thread sequentially executes the inner loops, which means that we have not done any aggressive optimization to the kernel. And we're going to discuss the performance of this kernel in the performance evaluation part. Let me give you an overview of BigStab implementation for GPU. The original CPU version uses LAPACK dgesv, which solves a linear system using an ADO decomposition. For the GPU part, we use a combination of cuBLAST and CUDA solver to do the similar operation on GPU. And please note that for this particular part, in the current implementation, we only prepare the full CUDA version, which we call low-level version, and call it from chapel. And finally, we came up with a data transfer optimization technique where we hoist the CPU to GPU data transfer, and we also defer the GPU to CPU transfers. This optimization allows the GPU to keep the data as much as possible, and we will discuss the impact of this optimization in the performance evaluation part. We evaluated the performance of our CHAMPS implementation on the following three platforms. The first platform is Cori-GPU cluster at NASC, which has Intel Xeon Skylake CPU and NVIDIA Volta 100 GPUs. The second platform is Summit at ORNL, which has IBM Pro 9 CPU and NVIDIA Volta 100 GPUs. The third platform is a single node AMD machine, which includes Ryzen 9 CPU and Radeon RX GPUs. We used Chapel 1.22 because recent versions of Chapel could not compile CHAMPS application. And for GPU compilation, we use NVCC version 11 and AMD LogCamp 2.9 plus HIP 2.8. And also for BigStab for CPU, which is a linear solver port, we use the IBM ESSS library on Summit and the Intel MKL on the Cori and AMD machine. Okay, what you see here is the end-to-end performance improvement on the three platforms. And please note that in this evaluation, we only use a single node with a single GPU. And first of all, we see great performance improvement over the CHIUW CPU version. For example, on Cori, we get around 29.5 times performance improvement over the CPU version, which is great. Also, our GPU implementation has three variants: low-level version, mid-low-level version, and mid version. And please notice that there is no significant performance degradation even when higher-level GPU API is used. We also see the significant performance impact of the data transfer optimization, which gives the 2.25 performance improvement on Cori, 1.39 performance improvement on Summit, and 1.17 performance improvement on AMD machine. And we explore the possibility of further optimizing this application on GPUs. The table shows relative performance number normalized to the assembleLHS port without data transfer optimization. And as you can see, the data transfer optimization significantly decreases the data transfer time. However, now that the data transfer is optimized, the kernel time accounts for the most of the entire assembleLHS port. And to analyze the performance of this kernel, we used the NV profiler and collected several hardware counters. For example, we noticed that the achieved occupancy was around 12%, which means that the GPU was less busy. And also for the global memory accesses, we noticed that the global store efficiency was not very good because many of global store transactions were not coalesced. So to further optimize this kernel, we plan to do the hierarchical prioritization to increase the occupancy. And also we perform global memory access optimization, particularly for the store operations. And finally, let me talk a little bit about the productivity evaluation. The table shows the source lines of code added for enabling GPU execution. As you can see, the use of GPU API significantly reduces source lines of code for the host part, and also mid-level API further reduces the source lines of code for that part. In this application, we identified that the use of the GPU jagged array was quite effective to reduce source lines of code at the mid-level. Okay, so in this talk, we discussed our experience in accelerating CHAMPS on GPU using our GPU API and the GPUIterator module. And we get a really nice performance improvement on the three platforms. And for the future work, we are going to optimize the GPU kernel. And also we are going to accelerate another solver, which is a LAN solver, and see if we can get a similar performance improvement. And we'd like to thank the CHAMPS team for this collaboration. And also we'd like to thank the Chapel and the Habanero team for their feedback on the design and the implementation of our GPU API and the GPUIterator module. And this research used the NASC and the ORNL computing resources. And finally, the version 0.4 of the GPU API and GPUIterator modules is available on GitHub. If you're interested, please go to our repository and see the detailed documents. And also, our community is growing. If you're interested in accelerating your chapter application on GPU, please feel free to contact us. Thank you very much for your attention.